السلام عليكم.
وعليكم السلام.
والصلاة والسلام على رسول الله. Yes, let's start chapter 8. Chapter 8 title is what? What's the title?
Chemical bonding.
So, what are we going to talk about?
Chemical bonds.
How the chemical bond is taking place. This is called chemical bonding 1. So, what do you expect chapter 9 will be?
Chemical bonding 2.
Chemical bonding what?
2.
2. Yes, of course. Chemical bonding 1 and chemical bonding 2. All right. And here we're going to talk about so many things. First, we're going to talk about Lewis dot symbol. Lewis dot symbol. And this Lewis dot symbol is very easy with dot symbol. Get your periodic table.
دكتور
Yes.
بس المعذرة عندي سؤال الحين شابتر 7 معنا؟
اليوم ولا في ايش؟
لا المنهج لأن كان في واحد من أخوياي يقول إنه ما هو معنا.
شابتر 7
يقول إن إحنا ذاكرنا بس إنه ما راح يدخل معنا بالاختبار. هل صحيح ولا؟
لا طبعا غير صحيح نهائيا. اللي
تمام.
7.7 ما هو معنا.
سيكشن شابتر 7.
Yes.
تمام.
Lewis dot symbol. I want you to get your periodic table. Get your periodic table out. Look at it. And then I want you to tell me what's the meaning of valence electron?
The lastmost electron.
Last what?
The lastmost electrons on the last level.
No. Which
Electrons
level? Last what?
orbital.
Which orbital?
And the element.
The last sp orbital, not any electron, only sp electrons. Is this clear? All right, the last sp electron. This is why, for example, if we have something like bromine, Br, what's the structure of bromine?
1 is 2.
1 is 2, 2,
2 is 2.
6.
2.
Yeah,
B6.
3 is
3
2.
is
3p6. Go ahead. 4 is 2. 3d what? 10. 4p7. What's the total number of electrons in Br? What's the atomic number of Br?
35.
What?
35.
35.
35. Very
Cannot
good.
be 7, Dr.
Doctor?
P.
Should be B6 is 1.
What again?
We can't have B7.
Oh,
B5.
wrong. Oh, something in my mind. That's why I wrote 7. Okay. It's actually 5, not 7. This is 5. Oh, I'm wrong. Yes, I agree. Okay. Okay. What's the atomic number?
35.
35. How many total electrons?
35.
35. If it's the VR without any charge, it will be 35 electrons. How many valence electrons do we have?
9.
7. That's why I wrote 7 there. Why are we saying 7?
Last
Because S and B have 7
Group
electrons.
17.
Of bromine. It's 4s, 2 plus 7. What do we call the rest of the electron, which is how many?
28.
28. What do we call them?
Core electrons.
Core electrons. You have to memorize these important definitions: valence electrons and core electron. Of course, this is the electronic structure of Br. Is this clear? Now, the Lewis dot symbol take the valence electrons of the element and put it around it. Like, for example, bromine, Br. How many electrons do we have in bromine? How many valence electrons?
7.
7. And that's why the way they put it in Lewis, if it's 1, they will put it like this. 2, like this. 3, like this. 4, like this. If it's 5, like this. 6, like this. 7, like this. And there's no 8, so I'll stop here. This is the electronic structure, or the Lewis dot symbol for bromine. What's the valence for all halogens? 7. Exactly. Okay. So how are you going to draw the Lewis structure or the Lewis dot symbol for chlorine?
The same thing.
Exactly. Same. Is this acceptable?
Yes, it is not restricted to any point.
How about chlorine?
The same.
This
How about iodine? And so on and so forth. Is this clear?
yes,
And how about if I want to draw it for sodium? What's the valence of sodium?
1.
One.
Only one.
And then what? Only 1. Okay. How about if I want it for iodine minus? What are you going to do?
Add 1 electron.
I add 1 dot.
This means what?
8 electrons.
8 dots.
How about if I want Na plus?
Remove 1 dot.
Deduct 1.
This means how many electrons should I put?
0 electrons.
0. Exactly. Is this clear? Good.
Yes.
Doing this, you will draw this structure. Look at the main group. These. Why do I say main group? I'm talking about what? Main group elements. What do you mean by main group?
S and P.
S and P group. Can you draw the Lewis structure for S and P group?
Yes.
For alkaline, how is it? 1 electron.
1 dot.
What's the name of this group?
Alkali earth.
Kali earth. Okay. How about this? How about this group? What's it called?
Noble gases.
Noble gas.
Gases. They are the same except helium. What's helium?
2 dot only.
Only 2 dots.
2 dots only, and we put them together, not like, for example, Be or Mg, because it's noble gas, and it cannot take more than 2. Very good. Always the valence of halogen is 7, oxygen group is 6, so on and so forth. So we have to know the valence number. What's the valence of alkali metals?
Plus
One,
What's the valence for alkaline earth?
2.
2,
2,
2. What's the valence for halogen?
8,
7.
7,
No, halogen 7, yes. For noble gas 8, halogen 7, 6, 5, 4, 3. That's it. These are the valence electrons. Is this clear? Good.
yes, clear.
Very quickly. What's the structure of F minus?
It will be 8 dots.
8
How many?
8
8. Exactly. And we should write what? Minus. Good. How about K plus?
without
0
any
dots.
No dots at all. Very good. How about S2 minus?
plus
What is this?
It will be 8 dots.
8 dots.
So yes, the 6 have S2 minus, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. Okay, how about chlorine minus?
it is 8.
8.
Okay. Now, what do you call chlorine and Cl minus and S2 minus? What do you call them?
Ions.
Yeah, they are all ions, but what do you call them also?
Isoelectronic.
Isoelectronic. You have to memorize the name. Very good. Good. Next. Lattice energy. Lattice energy. Lattice energy is an energy that we use, and we're going to call it capital U. Capital U. What is lattice energy? The lattice energy is the energy required to take solid ionic compound to make it gaseous ion. And delta H for this reaction is called what? U. Read the name. What's the name?
U.
The name.
Lattice.
That is energy.
Energy. Define to me what's lattice energy.
The energy required to change the solid ionic compound into a gaseous ion.
Gaseous ion. Give me example of NaCl. Give me the reaction for NaCl.
NaCO plus energy of heat
Yeah,
to Na plus and CO minus
yeah, but NaCl what?
plus
Solid.
You must write solid ionic compound. Into what?
gaseous Na ion plus
Na plus, what's there? Gas.
gaseous
And then plus
plus CO minus gas.
C what? Cl
Gas.
minus gas. What's the energy for this reaction?
Minus 56.
No, we don't know what's the number. It is what?
U.
U.
Lattice energy.
Lattice energy. U is always positive. Why is that? Because you are breaking bonds. Whenever
And
you break bond, you need energy.
endothermic, right?
The bond is like a stick. لو عندك عصا, you want to break the stick, العصا. You need energy to break it, right? So whenever you break bond, you need what?
Energy.
Energy.
Energy must be, delta H must be what?
Positive.
When you make bonds, what? It's the reverse of breaking bond. When you have, for example, Cl2,
Release energy.
Cl2 goes to 2Cl. What's the energy here? Is it going to be positive or negative? Delta H.
Negative.
Cl2 goes to 2Cl. Delta H will be what? Always positive. On the other hand, 2Cl goes to Cl2. What's delta H?
Negative.
Negative. Is this clear? So whenever you break bond, delta H positive. Whenever you make bond, delta H is what?
Negative.
Good. Now, what are we doing here? We're breaking the ionic bond. We're breaking the ionic bond between NaCl. Is U going to be positive or negative?
Positive.
It will be always positive. How about Na plus Cl minus goes to NaCl? What will be the energy of this reaction?
Negative. Because making.
It will be the negative of the lattice energy. So the lattice energy is always positive for this reaction because we define it as the energy required to make solid ionic compound goes to gaseous ion. And that's why it is positive. But if you make the ions like this, then it will be negative U. Is this clear? Good, I hope so. We know what's the meaning of ionic bonding.
Metal and non-metal.
Exactly, between metal with what?
Non-metals.
Non-metal.
How does it take place? First, the metal what?
Then the non-metal.
The metal lose lose electron to make what?
A cation.
Exactly. And what will happen to the non-metal?
Anion.
Anion.
Gain electron.
Gain, exactly. Gain electron to make.
Ion.
And then what will happen to the cation and the anion?
Attract.
Attract each other, and that's how the ionic bond takes place. That's exactly what's happening here. What's happening to the K?
Lose electron.
Okay, what happened to iodine?
Gain electron.
Take a look.
Okay, what do you call this reaction?
Reducing.
What do you call this reaction? We just took it in chapter 7. What type of reaction is this one?
Oxidizing.
Read this. What did I write?
Ionization energy.
What type of ionization energy? Which ionization energy? First,
First ionization.
what do you call delta H for this reaction?
Lattice energy.
No. When iodine gain electron, what do you call this?
Electroaffinity.
Electron affinity, electron affinity. And what's delta H for this reaction? Minus electron affinity. You remember chapter 7, we talked about electron affinity, and I told you that delta H is always minus the electron affinity. All right? So
Right.
here, when these become like this, what will be delta H for this one? What's delta H for this one?
It will be IE minus EA.
Exactly. And by the way, he wrote here, or it's written here, electron affinity of iodine. No, the electron affinity of iodine is plus 295. Be careful. This is minus electron affinity of iodine. Is this clear? Clear? Electron affinity, if it's positive, then delta H is negative, and if this is negative, this delta H will be positive. Is this clear? So this is actually minus electron affinity of iodine, which is minus 295. The electron affinity only is 295, positive. All right? Good. Now, the lattice energy, we define it. What do we call this energy?
Lattice energy.
Why? What are we doing?
Breaking.
Solid ionic compound.
Gaseous ion.
Change gaseous ions.
Goes to gaseous ions. Exactly. What do you call this? Delta H equal to 632. What do you call this?
Lattice energy.
What?
Lattice energy.
Lattice energy. Lattice energy. Clear? Good. Lattice energy has been calculated for so many compounds. You can look at this list. Okay? Do you remember? Look at the numbers. Don't memorize any number. Don't even just read the numbers, and I want you to compare the numbers. Look at lithium fluoride and lithium chloride. What's the number for lithium fluoride?
One thousand.
1017.
What's it for lithium chloride?
860.
860. Tell me why lithium fluoride is more than lithium chloride. Why?
Maybe listen, search for floor.
You remember in chapter 5, E, which is the electrostatic force, is proportional to what?
The charge term.
Q1
Charge and the distance.
Q2 divided by distance, right? Okay, distance squared. Actually, it's like this. All right? Tell me why now lithium fluoride is more than lithium chloride.
Doctor,
Yes,
higher charge.
What?
Doctor,
Yes.
because the distance between الأتومات ثنتينهم اللي تحت هو أقرب من بعض فطريقة فكهم بتكون أصعب
Which
إلى
one?
أيونات.
Look at the numbers.
The size of floor is less, so the distance is less.
What's the distance between two atoms? If this is lithium and this is fluorine, where is the distance? It's from the nucleus to the nucleus. Okay? Which distance? Distance 1 or lithium chloride, which is from lithium to chloride ion. This is the D2. Which one is bigger, D1 or D2?
D2.
D2,
D2 is bigger. Why?
because the number is less.
No. Yeah,
Because
but
the atom is bigger.
because the chlorine is bigger than fluorine. Exactly. And that's why this one, yes, D1 is smaller than D2. As a result, which one will be stronger? E for lithium chloride, lithium fluoride, sorry, or E for lithium chloride? Which one is bigger?
E for fluoride.
Exactly. Because the D1 is smaller than D2. Is this clear? Good. Let's compare something else. Let's compare, this is, yes. Let's compare MgO compared to sodium fluoride in NaCl, or even lithium fluoride. Fine. Let's compare MgO and lithium fluoride. Like, what's the value for lithium fluoride?
1070.
1070. What's the value for MgO?
3890.
3890.
Assume that the lithium fluoride, assume it's not exactly, but they're very close. Compared to MgO, the distance from the nucleus to the nucleus, this distance is almost the same. Almost. They are very close. D here, I'll call it D3, and D3, they're almost the same. Okay, why the value for MgO is much greater than lithium fluoride?
Because the difference in charge.
The difference in charge. Okay, compare this number to this number. What's the ratio between them?
Almost 4 times.
Almost, very good. MgO is much higher because E is what?
Q1, Q2.
MgO, for MgO, what's E is proportional to what?
2 times 2.
Times 2 minus divide by D. Okay, compare this one to E for lithium fluoride. What is
+1 times -1.
+1.
How did you know it's the distance is equal?
Approximately, I told you. You are not. You don't know it. I am telling you now. Okay, and this is approximate. It's not exactly, but they are very close. Let's say. Times divide by D squared, and then in all cases, this is 4 times. Is this clear now? Okay, that's why let's compare now. Which one you expect to be higher E? Lithium fluoride, lithium iodide, or sodium iodide? Which one is bigger?
Sodium iodide.
Sodium.
Oh, bigger U. A bigger E, the energy.
Lithium iodide.
Lithium iodide. Bigger lattice energy. Okay, why? 732, 686.
It is smaller.
Because
size.
iodine is the same, but lithium is smaller than sodium, right? How about lithium iodide compared to potassium iodide?
It is stronger lattice energy.
Oh. Is it not lattice energy? I'm talking about even the lattice energy. It's not stronger. In fact, it is less.
It is smaller.
By the way, this is not the lattice energy. It is actually energy of attraction. This is also smaller. Why?
The distance is greater.
Okay. Compare it now to this one, lithium fluoride and MgO. They're almost the same size. Can you see the size? That's the exact size. They are very similar, almost. But this one has +2 charge. This one has -2 charge. Okay? And because of that, look at the numbers. Is this clear? Good.
I don't understand. Can you repeat?
What again?
I don't understand. Can you repeat?
This is, look at the numbers, the force here between them. This is the energy between them. It depends on what? The charge and the distance, which is from here to here. What's the charge of this one?
-1.
What's the charge here?
-2.
+1. Why are you saying -1 or?
Oh, you mean the left one? Okay.
What's the charge in here?
-1.
This is -1 and this is +1. And what's the distance? Approximately, it's this distance. This one. That's the distance between them. Good. And this is why the energy is 1017. Look at this one. What's the charge on Mg?
+2.
What's the charge on O?
-2.
-2. The charge is the distance from the radius to the radius. This is the radius and this is the radius. Look at the total here. Is this close to this one?
Yes.
Yes. The total energy is almost 4 times because the D here and the D here are almost the same. Almost.
دكتور
Yes.
في قانون يقول G times Q over D square.
Yeah.
هو هذا بس احنا شلنا الجي صح اللي هو الكونستنت.
الجي ايش هي الجي؟
كيف؟
ايش هي الجي؟
كونستنت القوة اتوقع.
صح.
ثابت الكون الجاذبية.
Yeah, no, الجاذبية. If it's الجاذبية, wrong. If it's a constant, it is a constant. Yes.
It's constant.
Not جاذبية, not gravity.
ثابت كلام.
Okay. All right. Is this clear now? Now let's compare this one, MgO. Look at the periodic table. Compared to CaO, compared to SrO. Which one will have the highest lattice? Energy force between them.
MgO.
MgO, and then
CaO.
CaO.
Why?
SrO.
Why?
Because Mg has a bigger size.
MgO. What? Mg is what?
Is smaller.
The distance between them is the radius of O with the radius of R. So this is the distance from the radius. It's the radius plus the radius. Which one is bigger? This radius of Ca or Sr or Mg?
SR CA.
The oxygen is the same. And that's why this one has the highest force. Good. Let's compare one more. Let's compare MgO to MgF. And of course, which one will have a higher force between them?
MgO.
If this is X, then what will be the value for the force for MgO approximately?
4x.
3 times? 4 times?
No.
2 times.
2 times, exactly. Why 2 times?
Because the charge of O is -2 and the fluorine -1.
It's +2 and the Mg is +2, so there is no effect. But this one, it was -2, this become +1, -1. And that's why approximately the force is twice as much as this one. Is this clear? Now,
Doctor,
yes.
can you go back for the slide before? Yeah, how we convert -0.23 to 1017 kilojoule?
This is numbers, you got it from this table. These are the number. 1017, and for MgO, 3890. Can you see these numbers?
Yeah.
Not calculation, because this is proportional to, this is just, he put the charges and the distance or the radius of each element. But the total, this one is, we take it from the value, from the table. All right?
I can't calculate the value.
We did not give you the how to calculate the value. You can calculate it, but you need some constants.
Okay.
Next, we're going to what's called Born-Haber cycle. Born-Haber cycle. I want you to memorize the name, Born-Haber cycle. This is for ionic compounds, ionic bonding and ionic compound. All right. Read the name. What's the name again? Born-Haber cycle. Why did they call it cycle? Look at the structure here. Why did they call it cycle? Because it's a cycle. Can you see the cycle? Yes? Hello?
Yes, doctor. It's like a loop.
Loop. It is loop. That's why they call it cycle, because it is actually a loop, exactly. But this is exactly similar to Hess law. What's Hess law? Remember Hess law in chapter 5?
The energy.
Yeah, but what's Hess law? You calculate the energy of a reaction from what?
From the equation.
From
another reaction.
From other 3 or 4 reactions, or 2 or 3 or 4 or 5 reactions. Look at this one. If you go from here to here, this is a reaction. Or if you go from here all the way to here, you're going to go to the same reaction, but you'll go through many steps. And that's why this reaction, it must be equal to all these reactions. Is this clear? Okay. What do I mean? Now, what is, if you go from this compound, solid compound, into gaseous atom, what do you call this reaction?
Ionization.
No, from solid compound to gaseous ion.
لا لا تسأل.
Late.
It is
Late energy.
what's the letter that we use for it?
You can.
U capital.
U capital.
And I know the value for this U capital, which is given here, is always what?
Positive.
Positive.
That's the lattice energy. Is this clear? It's all positive. And this is the energy required to take something like, give me the reaction for lithium fluoride. Lithium fluoride what?
Solid.
Into what?
Lithium.
Lithium ion and fluorine ion.
Minus.
Yes. Good. Okay. What did we do here? We took NaCl into what?
To Na gas and Cl gas.
So what do we call this energy?
Lattice energy.
Good. Now, if you go from NaCl solid into Na solid plus half Cl2, we told you in chapter 5, if we go from here to here, the red pen, what's the energy to make this reaction?
Mine.
It's the heat of what?
Heat of
Formation.
Formation. What's the heat of formation? Define to me what's the heat of formation, chapter 5.
The heat produced when forming 1 mole of a compound at STB.
From what? Yeah, at STB. From what?
It's
elements.
constituent elements.
From naturally occurring elements. That's how these elements are occurring. And that's why the red arrow here is the delta H, F. What will be the blue arrow?
Negative delta H of formation.
Negative. Negative this one.
Delta H reaction.
Is this clear? Good. I'll take this away because it's negative. Exactly. Good. Next, let's go from this one, in this reaction. So I finished with reaction 1. Let's go with reaction 2. What are we doing? We did not do anything to chlorine, right? All what we did is we took sodium solid into sodium gas. What's this reaction? Chlorine, we did not do anything to it. If you take solid into gas, what is this reaction called? Heat of formation. What's the heat of formation? Come on. It's making this compound from what? Not compound, this time it's element. From what?
It's natural occurring elements.
Naturally occurring, exactly. And we did not include anything about the chlorine because nothing happened to the change in chlorine. Okay, in reaction 3, what do we call this heat?
Formation also.
Formation.
Heat formation of what? Chlorine. Look here.
Chlorine.
We did not do anything to sodium. Did we do anything to sodium from here to here?
No.
Okay, so what did we do? We took half Cl2 and make it Cl. So what's this heat? Heat of formation of chlorine atom, chlorine gaseous atom. Why? Because we are making it from what?
Two.
Okay. Are you following? Okay, what did we do in reaction 4?
Ionization.
Why? Look at the chlorine. What did you do to chlorine in reaction 4?
Nothing.
Nothing. So, but for sodium, what did we do?
We take one electron.
We took one electron. That's the energy for this one is called what? The first ionization energy, EA1. Is this clear? Good. And let's look at equation 5. We did not do anything to sodium plus. It is sodium plus here. What did we do then?
Add electron to chloride.
We add the electron to what?
Chloride.
To make it Cl minus.
Zero.
What's this reaction called?
Electroaffinity.
Electron affinity of chlorine, and we have to change the sign. Always delta H is equal to what? Minus electron affinity. Clear? Good. So from his law, U equal to what? Is this clear?
Yes.
Can you repeat?
U, which is the reaction going this way, is equal to 1, 2, 3, 4, 5, because we are going to the same way, but in another way. And that's why we call it Born-Haber cycle, because it's a loop, and we're going from one side or the other side. The energy to go from here or from here to here to here to here to here is the same like this one. That's why U in this case, which is this one, is equal to reaction 1 plus 2 plus 3 plus 4 plus 5, the value for this one. So 1, 2, 3, 4, 5. And that's why we have the lattice energy equal to the heat of formation of NaCl plus heat of formation of Na gas plus heat formation of Cl plus heat of formation or electron affinity of Na minus electron affinity of Cl minus. It's numbers. This one.
Doctor.
Yes.
Will we use the long method?
What do you mean by this? No, what I want to do in the question, I will give you all these numbers except one of them. So maybe I can give you 1, 2, 3, but I don't give you 4. Let's assume I don't give you 4. And I give you 5, the value for 5 and U. Then can you calculate what's 4?
Subtract 1, 2, 3, 5.
U minus all these numbers. Exactly. Is this clear?
Doctor.
To notice one more thing, that this one is reversed. This one is reversed. Why? Because the heat formation is to make this one. We're doing here the reverse of heat formation, and that's why we reverse the sign here. But here, the heat formation is okay because we're going from solid to gas, and that's why we keep the same heat formation for this one, same heat formation of this one. I want you to notice these values. So, Doctor, let's do this problem. I'm sure we can solve the problem like this. Okay, if you are given these values, we're going to do the cesium fluoride now. Cesium fluoride. What's this value? Electron, ionization energy of Cs. Write the reaction for electron, for cesium, for ionization energy. What's the reaction? Cesium. Yes.
CO.
gas. Oh, ionization energy.
Plus electron.
Plus electron give you
Cl minus.
CS.
CS
It will
plus.
produce electron.
Goes to CS plus gas plus electron. Okay. And the energy will be delta H for this one. What's delta H? Equal to 376. Good? Okay. What's this? Read this.
Affinity. Electron affinity.
minus 3 4.
What should I write? Cl what?
Cl plus electron.
Plus electron to give you
Cl minus.
Cl minus.
gas. What's delta H?
Minus 3.
Yes, always is the negative of electron affinity. Clear? Good. Next, what's the heat formation? Give me reaction for heat formation of CS gas.
CS solid.
CS solid goes to
Plus energy.
CS gas.
Gas. Exactly. What's delta H for this reaction?
76.5.
Yeah. Give me reaction for this one. Heat of formation of Cl gas.
Cl2.
CS Cl2.
Half Cl.
As goes to what?
Cl.
Cl gas. What's delta H for this reaction?
Half of 1.
No?
1 to 1.7.
1 to 1.7.
Why? Because heat of formation of this one, we're making 1 mole, and that's why it is 1 to 1.7. If I do for this reaction, Cl2 goes to 2 Cl gas. What will be delta H for this reaction?
Minus.
Cl2 gas goes to
Multiply by 2.
what?
Multiply it with 2.
Multiply
Minus
by 2. 2 times what?
1 to 1.7.
Exactly. That's why the heat formation is like this. Good. Okay, so we need to make 1 mole of the product, not 2. Okay, good. Last one. What's the last one? It's heat of formation of CSCl. This is heat of formation of CSCl. But I'm going to reverse it. I will write CSCl solid goes to CS solid plus
Cl gas.
Half Cl2 gas.
half Cl2 gas. What's this? What's the delta H for this reaction? For the last reaction?
442.8.
Plus or minus?
Plus.
Plus 442.8.
Doctor, why reverse the reaction?
I'll tell you why. Now, do you know how to do Hess law?
Yes.
Yeah. What do you do with Hess law? You cancel anything is available in both sides. CS gas, is it available anywhere else?
In the third one.
Yes.
Very good. Solid.
Yes.
Let's call these numbers. 1, first reaction, second reaction, third, 4, and 5. What else can you cancel?
Half Cl. Half Cl.
Half CO2 from 4 with what?
5.
Okay, what else can you cancel?
CO gas, CO gas.
With 4.
What else can
And
you cancel?
Electrons.
Electrons you can cancel, exactly. What will be left?
CS plus, CO minus, and CSCO.
The SCl, what? Solid goes to what?
Go to CS plus, CL minus.
The Cl minus.
Gas.
What do you call this reaction? What do you call this energy?
Lattice energy.
Lattice energy.
It is lattice energy. Is it U or minus U?
U.
Why? Because we take solid into gaseous ion, which is the same. So it is U. Okay. Can you calculate what is the value of U using the top numbers?
We'll add them.
Value. Calculate it. Use your calculator.
Six 38.
6 what?
38.
No. Recalculated.
668.
668.
667.
Born-Haber cycle now. Old Born-Haber cycle, the one we are looking at. That's the question that we did, and the answer is 668. Good. Okay, let's go, move. Okay, Lewis structure. Lewis structure and Lewis theory of bonding. Lewis says, very important name, Lewis. Did we see this before? We saw this one, right? Lewis dot symbol. Did we see this before? What's Lewis dot symbol? What's Lewis dot symbol? Distribute the valence electrons around the element. Like for example, Mg. What's the Lewis dot symbol for Mg? Like this. You remember it?
Yes.
This is the Lewis dot symbol. Lewis dot symbol. Don't forget it. Clear?
Yes.
That the elements will always like to make 8 electrons around it. 8 electrons around it. And that's why, for example, F does not like to be like this. It prefers to be what?
With 8 electrons.
7 electrons.
Like this. All right. So he says that, of course, there is exception. Hydrogen would like to have how many around it?
1.
1.
2. 1. And that's why.
Nothing.
No, 2. Hydrogen now has 1, but when there is another hydrogen,
like helium,
it will be like this. That's why hydrogen would like always to be 2 electrons around it. Okay, I repeat one more time. Look, let's go to the next slide. Has 1 electron, and the other hydrogen has 1 electron. And Lewis says that hydrogen will always like to have how many? 2 electrons around it. And that's why this hydrogen will come with this hydrogen and make 2 electrons, whether we draw it like this, or we draw it like this, or we draw it like this. It doesn't make any difference. But
A covalent bond, right?
Lewis says that hydrogen, what? Again?
Covalent bond.
Covalent bond, yes. This is all covalent bonding, exactly. Is this clear? So hydrogen does not always would like to have 2 electrons around it, and that's why it will bond with the other hydrogen. But if there is hydrogen with fluorine, the fluorine now would like to have 8 electrons around it. How many around the hydrogen?
1.
1. And how many around the fluorine?
7.
7. If they share these 2 electrons, what will happen? How many electrons will be around the hydrogen?
2.
2. And how many about the fluorine?
8.
8. And both will be happy. We call this sharing of electron, we call it covalent bonding. Covalent bonding. And we call this bond covalent bond. Covalent bond. And Lewis says that hydrogen would like to have how many electrons around it? 2 only. But other elements would like to have how many?
More than
8. Is this clear? That's why when we go to fluorine, with fluorine, what will happen? This fluorine has 7. This fluorine has 7. What will happen if they share these 2?
There will be 8.
8 around each one. And how should we draw the structure? We can draw it like this. We can draw it like this. And we can draw it like is there a difference between 1, 2, and 3? Is there any difference between 1, 2, and 3?
The same.
No, the same.
It's the same.
We call this one, if it's like this, we call it single bond. Single bond. And it makes single covalent bond. Covalent bond take place between non-metal with what?
non-metal.
The non-metal.
Good.
Or metal.
And the elements would like to have how many electrons around it?
8.
8. Except?
Hydrogen.
8 except electrons, except hydrogen. 2, 4 hydrogen. Is this clear? Good. Let's try it for oxygen. How many around the oxygen? 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4. 5, 6. How about the other oxygen? 1, 2, 3, 4, 5, 6. Now, if they share the electrons, how can we make them share 8 electrons? They will share it like this. We will put 2 electrons, 2 and 2, and O with 2 electrons, 2 electrons, and 2 electrons. Now, how many electrons around this oxygen?
8.
8. No, 8. And around this when they share. And how many around this oxygen when they share? 8. Why? Because share like this. So how can we draw them?
Double bonding.
Two lines.
Two lines.
And now, how many electrons around this oxygen?
8.
8.
And this one,
8.
8.
what do we call these electrons?
Double.
Covalent.
Shared electrons.
Shared electron.
Shared electron or bonding electrons. Is this clear?
Yes.
And
يعني دكتور
the outer electron, what do we call them?
Lone pairs.
Lone pair. Lone pair. Don't forget this. Where is the bonding electrons in F2? Where is the bonding electrons?
The ones in the middle.
The middle. These are the bonding electrons. What do you call these electrons?
Lone pairs. Lone pair.
Pairs. How many bonding electrons we have in F2?
1.
How many electrons? How many bonding pair?
1.
1.
Bonding pair in F2, how many? 1. How many in O2?
2.
2. I hope this is clear. Good. Let's do one more thing. If we have nitrogen and nitrogen, nitrogen has how many?
5.
5. And then the other nitrogen?
5.
5. How many electrons we need extra to make it 8?
3.
3.
So what I'm going to do, I'm going to share 3 electrons here and 3 electrons here. When they share this one, how many left for the first one? 2 we'll put here and 2 we will put here. So now, how many electrons after we make the bond? How many around this nitrogen? How many? 8. And how about the nitrogen?
8.
8. How many bonds did we make?
3.
What?
3 bonds.
3.
How many electron pairs? A bonding pair between them. Bonding pair. How many bonding pairs?
3.
Yes. Also 3, because each one is a pair. 3 bonding pair. How many lone pair are on this nitrogen? 1. And how about this nitrogen?
1.
1. I hope this is clear. Very good. Of course,
Doctor.
we have what's called, just a second, we have what's called single bond. Give me example of single bond.
Chlorine.
2.
Chlorine.
Single bond.
Oxygen.
Oxygen.
Or triple bond. Give me example of triple bond.
Nitrogen.
Nitrogen.
And 2.
Without any question, which one you think is stronger? A single bond or a double bond or triple bond?
Triple.
If we have this one and with something else, but I'm just concentrating in part of it. Which one of these 3 will be the strongest bond?
The third.
Third.
Be the strongest.
Third.
Which one will be the longest?
The first.
1.
This is the strongest, and this one is the weakest. Right? Now my other question is, which one is the longest?
The first.
Which one is the shortest?
Third.
The third.
Is this clear? We call them multiple bond. What do you mean by multiple bond? Either double
2 or
bond,
3.
More than 2.
triple bond. Okay. Look at the structure. See? How many bonds between carbon and oxygen in here? How many bonds?
2.
2 bonds.
2.
How many electron bonding pair?
Two.
So 2. Okay. Okay. How about this one? Same thing.
Two.
We can draw it like this. Good. Now, how many between this carbon and this carbon? How many bonds?
2.
Two.
Okay. How many bonding pairs? 2.
2.
And now, how many around the oxygen? This oxygen, oxygen 1. How many around it?
8.
8, which is happy. How many around this oxygen?
8.
8, which is happy.
8.
How many around this carbon?
8.
1, 3, 4, 5, 6, 7, 8. 8, which is happy. How about this carbon, which is already circled? 8. How many around this hydrogen?
2.
2.
Hydrogen does not want more than 2. Okay. Now let's concentrate on this one. How many electrons around this carbon?
8.
8. How did you know? Each bond.
Each line represents 2 electrons.
2 electrons. Or each bond is electron pair, so it's 2 electrons. Electron pair, 2 electrons. How about this carbon? How many around it?
8.
Hydrogen.
2.
How about this oxygen? How many around it?
8.
8. Why? 1, 2, 3, 4, 5, 6, 7, 8. How about this oxygen? How many around it?
8.
Also.
8.
Here. Good. Of course, always look at this table. Look at this table. Okay, this is the bond length. Bond length. Now, I want you to compare C with C, C with double bond C, C with triple bond C. Which one will be the longest?
The first.
Longest. Which one is the shortest?
The triple bond.
Short.
Triple bond.
Okay, that's the distance in picometer. What's picometer?
Times 10 to power 12 to minus 12.
Look at CC. What is it? 1, 5, 4. CC double bond 1, 3, 3. CC triple bond 120. Is this clear? Is this clear?
Yes.
Yes.
Up here, and I hope this is clear. Good. Let's stop here and go to the attendance very quickly. Okay, the attendance is open now. Take attendance and you can leave right away.
Doctor, when do you have the office hour?
After the lecture from here to 11.
Okay, thank you.
Doctor, can you please, if you ever find the chance to some of the homework questions, because the questions are kind of hard and the things we studied in chapter 6 are easy.